Okay, hi boys and girls. Another lesson from my basement. Today's lesson is basically designed to be a remote lesson. As we continue through this pandemic of COVID-19. But today I'm making it real. I'm trying to make it real for you, or if you haven't felt like it's real already by not being able to go to school. Hopefully we're going to get back to school in a couple of weeks. And I so look forward to seeing you guys again and sharing my experiences with you and, hearing about yours and what it's been like to live through the historic times. Now, when this all started back in, let's say, February, March, and we were all learning what this meant to be living through the pandemic, and we were learning about COVID-19 and the virus and how it was affecting people's lives, which it tremendously has. As you guys all know, we're stuck, not going out and not doing things that we normally used to do. So I got really interested in the math behind it. And you know me in math. I am a little quirky with that. And I relate a lot of things to math and numbers because I believe that it matters. And math really drove the train here, if you know what I mean. If you watch the CDC experts, back in March, April, May, when we were glued to the TVs and what was going on, they were very explicit in explaining or telling us we had to flatten the curve. And I thought to myself, what is the curve? What are they talking about? And so I started Googling, and I was also kind of obsessed with tracking the data and keeping track of the numbers of our city and our county, because we were living, we were only 2 or 3 miles away from the original hotspot where it all started. So we made history. Not that I want to make history, but we are living through historic times, and our area was being, scrutinized, and rules were put upon us of what we could and couldn't do. But why? What did that mean? Flatten the curve. And what was the goal of the CDC experts like Dr. Fauci and our political leaders, our president and our governor and our mayor? And what was their goal? What did that mean to flatten the curve? Well, for starters, what is the curve? So, of course, me in 7th grade math, I just do all these lines. I started to look up, researching, going to Google, and this day of technology, thank God, I started to explore what the curve was. And in relation to, how can I help you guys understand this? How can you guys understand what the curve was and what it meant to flatten the curve? So that's the intent of this whole lesson, is to understand and make it real about flattening the curve. And did all of our things that we have done over the last couple of months, were they actually effective? Did we flatten the curve? And this way, history, we tend to learn from history. We learn not to hopefully repeat ourselves in some regards, but maybe we did things right. And if the curve did flatten, then we have to kind of conclude that some of the things we've done were effective. So here's your assignments, okay? I kind of made up four kind of lessons, 4 different things. Some of it is for you to explore, but I'm going to guide you through these. I have 4 different kind of packets that explain, that are all going to be on the website, on my teacher, my Teams page. So for you to, download, print, whatever. But basically, it's a lot of it is exploring, and you guys coming up with. I'm going to guide you through this exploration, and then in the end, the last part of the assignment, I call it the 4th assignment, is bringing it all together in relation to our city of Yonkers and where we live in Westchester County. The city of Yonkers is in Westchester County, and I have the data for both, and you are going to become the experts, and you're going to tell us, did the curve flatten? You're going to come up with charting and graphing the data. But before we start that, I want to go through a couple of, review of linear functions and the rate of change in a linear function. And then I'm going to show you, because I'm sure you've never seen what they're kind of saying, this is a little bit of exponential function, meaning that the rate of the growth of the virus was exponential, meaning it was growing very fast. I know you know this term on your Instagram or your Snapchat or whatever it is you guys do. in social media stuff, you've heard of the expression go viral. Where do you think that came from? Something that goes viral is growing very fast, okay? And so, you know, my goal is my videos, my math videos, gonna go viral. What do you think? Anyway, I want to review some of the topics with you and introduce you to an exponential function and what that kind of looks like. And then the first lesson is you have to watch 2 videos. You're going to watch a video of me just chit-chatting about this and doing the math again. And then the next video is, there's 2 videos of mathematicians, experts that show pretty cool little, like, you know, graphics, I guess, in the videos of how the virus grew. One is kind of cool, and he's from Britain. He's got this great accent, and I like his little graphics of himself and how he shows how the rapid growth of the virus. And then the second video, and one is 3 minutes long, the other one's I think 8 minutes at the most. The second video is a lot of mathematical terminology that I kind of just want you to hear. This is not about writing down notes. This is about listening and learning from, just take it all in. Take it all in and kind of think about what in the world is going on during our, you know, COVID-19 pandemic and how we are managing to survive. So I'm going to turn my camera like I've done before on my lessons. I'm going to, so you can look at just my hands showing you some of the review. Then I'm going to kind of show you my computer, and then I'm going to show you another thing about making, going to have a little fun activity that you can do. And if we get back into school, and I was going to say things get back to normal, if things get back to normal we wouldn't have to do this, but if we get back to school, I want to show you how to make a face mask. I was making them out of fabric, and so it's a little area kind of project that you're going to kind of design a little face mask company, and how you would cut them out, measure them, etc., etc. So I'm going to turn the camera. Give me a second while I move it to get onto my hands, and I want to review linear functions with you and what it means by rate of change, and then I'm going to introduce exponential. Okay, so sit tight. Okay, I've got my camera all on this crazy machine here, whatever you want to call this thing. Okay, so let's do a quick review of what it means to be a linear function and graphing linear functions. Okay, I think you would recall that I used to use the example of saving money. Okay, if you had money in the bank, and how it would, you know, if you kept it there, I mean, we can certainly add interest, but we're not doing that kind of thing. We're just doing a linear equation and what it would look like on a graph. Okay, so 2 types of linear functions. For you 7th graders, we are talking about the simple one. The first one we've learned in 7th grade was constant proportionality, which is this one. And where it was y equals mx, right? Where m represented the rate of change, right? Okay, the rate of change, or the growth rate or the decrease, whichever it is. It could be positive or negative, okay? And these are your variable parts that, you know, would, whatever you put in for x will create what happens to the y. So I made up the simple example, which I know I've used in class, was what if we were saving money every week? Had no money at all to start with, but we decided to save $20 per week, okay? The equation would look like this: y equals 20 times x, where x represents the weeks, right? And then the y is going to be your total money saved, right? So if I make a table of values like this, so y equals 20x, my rate of change is growth of 20 per week, right? X and so on. I could come up with my numbers. So at 0 weeks, remember our constant and proportionality problems? Okay, the constant proportionality, this is constant. It's a constant rate of change. At 0 weeks, I had no money. At week 1, it was 20 times 1, which is 20. At week 2, it's 20 times 2, so I have $40. Week 3, 20 times 3, I now have 60. Week 4, and so on. So we know that this is increasing by 20. Every step of the way, it went up by 20. So the rate of change is constant, right? Up by 20 and so on. Okay? Well, now let's take another example. What if dear old grandma started me out with $100 and said, here, I want you to open up a bank account. Start with 100. But then every week you are to put in $20. So now my equation is kind of changing a little. Okay? I have a start value that is not 0. Okay? But my rate of change is still going to be the same. So the equation would look like this. Y equals the $20 times X, number of weeks. But I started at $100, so plus 100. Okay? 8th graders, you guys were doing that. 7th graders was this. Just to kind of refresh your memory, this should not look unusual. All right, so I'm going to fill in this table. All right, wow. At 0, though, at 0 weeks, guess what? I had $100, so 100 goes there, right? At 1 week, week 1, I now have 120. At week 2, put 2 in here, 20 times 2 plus the 100, I now have 140. At week 3, 3 times 20 is 60, and the 100, oh, I'm at 160. So we always have that 100 there, right? And it's still, but the change is similar to this one. It's increasing by 20, right? So week 4, put a 4 in there, 20 times 4 is 80, so I get 180. Put a 5 in there, 5 times 20 is another 100, so now I'm at 200. Okay, if I jump all the way down to 10, let's go to 10. All right, 10 times 20 is 200, plus another 100, we are now at 300. Okay, so clearly, the way this is growing is the same. Plus 20, plus 20, plus 20, plus 20, plus 20, right? And then I jumped to get to there. Okay, both of these are linear. And why do I know they're linear? Because the rate of change is exactly the same. All right, I graphed them already to save some time because this is just a review, a refresher for all of you to get your brains back into linear functions. And I put them actually on the same graph. Let's see if I can get a better shot of this. Okay. Okay, so they're on the same graph, and I kind of counted out the bottom. The X is always the time, over time. Over time, things grow or not, right? They could decrease, but we're doing something with growth. So, and I counted them out weeks by 1. So here was 5, 6, 7, and then 10, so on. Okay. The y-axis is the total money saved, right? And I decided to count here by tens. So 10, 20, 30, 40, $50, then 100, and so on. So the first line at $20, right? At 20 per, let me see if I can get this a little bit wider. Okay, cool. If I did the first line, the first function, okay, was growing it 20, y equals 20x, right? Only 20, and we started out with 0. This is why 7th grade, remember constant proportionality. It went through 0, 0, and it increased. Week 1, I was at 20. Week 2, I'm up to 40. Week 3, I'm up to 60. Week 4, I'm up to 80. Week 5, I'm up to 100, all the way. And I connected it with my nice straight ruler, right, and made a perfect line. And the equation for this line was y equals 20x, right? Whereas this one, we started, the difference here is, look, I started at $100. So I didn't have 0 in the beginning, so I started at 100. So starting at 100, but I did the same thing. Week 1, it went up 20, 120. Week 2, over 2, it went up to 140. Week 3, it went up to 160. Week 4, 180, etc., up to 200. All the way over that at week 10, we would have made it to 300, okay? So notice these two lines. It has a constant, right? A constant rate of change. And that constant rate of change on both of them was by plus 20. What do you also notice about these two lines? The two lines will never meet because their rate of change is the same. So these two lines are parallel. Their slopes are the same. All right? A lot of terminology. All should be a refresher for what we did, we have done in class. Okay? Having this in your mind, think about this. Okay? Straight lines. It's not going to all of a sudden turn, right? Oh, there are certainly certain models of banking accounts and stuff that all of a sudden turn, because that's when things, you start to lose money or such. But in this two simple examples, y equals 20x plus 100, y equals 20x, they both have the same rate of change. They're both continually straight. These are linear, okay? Linear. Now, the virus. What do we know about the virus? Okay, I'm going to move on. The virus has been repeatedly talked about, the curve. So here's a picture, a graphic that I found that I liked, and you will see this probably when you do your little research too, about flattening the curve. The red, typical red, is not good. This is if the curve went up and up and up, went very rapidly, quickly up. This is called kind of an exponential growth. Okay? At some point, though, it does stop and turn and come down. And I believe that's when they call it logarithmic. And on your second video, the man touches on that a little bit. I'm not worried about you learning that. I just want you to understand, what does it mean that it's growing exponentially? Which, if you notice here, it started out down low almost by 0, but it actually isn't at 0, and I'll show you that in a minute. And then it just goes up, 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 nice and fast. Okay? And the goal, and I'm going to come back to this graphic in a minute, the goal is to flatten this out. Flatten it out, spread it out, so that over time, okay, there is not as many as positive infections. This axis, when I will come back to this axis represents the rate of positive, and the x-axis is over time. Okay? We will come back to this in 1 second. I want to share with you what exponential means. All right. Think of what the word exponential is, right? Something that is exponential. What does that sound to you? Okay? Something that is exponential. And it's usually exponential growth. Okay? Sadly, I've heard it used to describe fires. Oh, the fire grew exponentially. It just like took over the forest fires, like out in California. Zoom, they take it, it just rapidly eats away at the forest. Okay, that's exponential growth. All right, very quick. It kind of infers very quick action, something that's happening. What's the base or the root of this word? Is an exponent. And we know what an exponent means is to kind of keep repeating that multiplication, right? So the basic of the exponential value here, okay, is I'm going to do like the parent equation is y equals some base number raised to an exponent. Okay? And that the x represents the exponent. Okay? So I'm going to do a simple example of an equation, y equals 2 raised to the x. That's what this is an exponential equation, okay? The last ones we just did was y equaled 20, right? 20x. And the other one was y equaled 20x but plus 100. These two are linear. There's no exponent. This one has an exponent. Hence, it is called exponential growth. Okay? So, I already made a little paper. Let's take a look. So, Same concept. Make your XY table. Let's start with 0. If x is 0, wow, what does that mean? So over here, I'm going to go y equals 2 raised to the 0. All right, 8th graders should know this one. Something to the 0 equals anything to the 0 equals 1. So that value is 1. Y equals 1. Okay, let's do 1. Y equals 2 to the 1. Well, 2 to the 1 is simply 2, right? Y equals, we're going to do to the second. 2 to the second. Refresher, that's 2 times 2. 2 times 2 is 4. All right? Do 3. Y equals 2, and x now is 3. Okay? That's 2 times 2 times 2. 2 times 2 times 2 is 8. So I put an 8 over here. Right? This one's y equals 2 to the what? 2 to the 4th. So I put 4. And now keep going. 2 times 2 times 2 times 2. So actually, look what's happening. 1 to 2 to 4 to 8. So what do you think this is? 16. Okay? Now we're going to the 5th. So y equals 2 raised to the 5th. I'm not going to write it out now. 2 times 2 times 2 times 2 times 2. So what does that equal? 2 to the 5th makes 32. You get the concept? Okay? So it just keeps going and going and going and going, and you just keep doubling, right? So my next one, if I do y to the 6, y equals 2 to the 6, I'm going to double 32, so that's going to be what? 64. Right? And if I keep going again, so this makes 64. So then to the 7th, double 64 is what? 128. Okay. Go to the 8th, if I double 128, or guys, for those of you that need a refresher on your calculator, because I would, you can easily do this on your calculator too, but I want to show you the exponent part of it, okay? So if I want to go 2 raised to the 8th, enter, is 256, right? 2 to the 9th, okay? So 2 caret 9 is 512, which again, you could just double them, right? Let's get to the 10th. I want to show you what it is for 2 to the 10th. And I'm going to kind of squeeze this in here. Okay, so I'm going to go to the 10th. I'm just extending my little chart here. And if I bring my calculator back, because I want to make sure you understand what I mean by 2 raised to the 10th, okay? And again, we could just double, is 1,024. Okay, what do you notice about these numbers? Can I come up with a plus 20, plus 2, plus 1, or something? No, what did each one of these do? It doubled. It doubled. The growth here is rather rapid. Okay? And that's what they're saying, that a viral spread is exponential. But there is specifics about the way the numbers grow, okay? Now I'm going to show you the graph, and I did this prior too, so to save some time. Okay, so I made my graph out of days on the bottom, and I kind of spread it a little bit. I skipped, counted, 1, 2, 3, and so on. And then I had to do quite a bit of numbers here to get the height, and even then I didn't even get very high. So when I started plotting this is what's interesting about an exponential. The first one we plotted, okay, right? The first numbers I came up with was the exponent of 0. And anything to the 0 power is always 1. So it starts on the y-axis right at 1, right? It's not at 0. It's not 0, 0. It's right up in 1, okay? It's a 0, 1, right there. And then, so that's the first one. The second one was over 1 up to 2. Well, I kind of gave you a little wiggle room. And then the second one, if it was 2, if x was 2, it went over to up to 4, because I had to start with 10 at the box, right? If x was 3, it went up to 8. If x was 4, it went up to 16. If x was 5, it went up to 32. If x was 6, it went up to 64. If x was 7, 128. Look at what's happening. Do you see the spread, the distance between these dots? You see how quickly it goes. They're, kind of close, a little farther, a little farther, a little farther, a little farther. Ooh, here we go. Here we go. Okay? So I couldn't even fit up to, I got as far as 8. 8 was 256. Okay? 8 was 256. If I was to continue this up and up and up and up and up, I would be off the table and it would be growing, pretty significantly. Okay? So if we relate this or go back to the concept of flattening the curve, all right, guys, this is how it started. This exponential curve, zoom up. And again, it eventually has to stop, right? I mean, if everybody's overrun with the virus and then, or, the whole population, it's at that turning point that, okay, now we completely decrease. Then it goes down. Okay? So let's talk about this curve and what that means. You will be watching a video in just a little bit of time here to see, the differences of this. But let's talk about what this represents. Okay, so this is time. This is time of the spread, right? Of the viral spread. Dear COVID-19, right? So I could title this COVID-19. Graph. Okay, boom. There we go. The x is the time, right? And the y is going to be the number of positive cases. Got to be positive, otherwise you don't have it, right? Not that we want to have it, but number of positive cases will be your y. Okay, this dotted line is where the CDC experts had determined that at this line, a number of positive cases, was where our healthcare system could manage. From there down, our healthcare system, meaning hospitals, emergency rooms, emergency doctors, nurses, everything that requires in the healthcare system, okay? Number of respirators, numbers of the medicines that they were trying to determine would work. Anything below this, the healthcare system can handle. Okay? Anything above it, the number going above this, is when the healthcare system could not handle this. Okay? This is where if the disease was left to grow and grow and grow, okay, then that's when the hospitals could not handle. The hospitals would be overrun, okay, could not handle it. This would be extremely bad. So the healthcare people or the CDC people decided, how do we get to stop this spread, this growth so quickly? And they determined that the rate was so significant by being, just near each other, if you had a positive case, that you could rapidly spread this. So they came up with those mitigation strategies, okay? And the mitigation strategies, and you guys are going to do some work on that, mitigation strategies, such as 6 feet, social distance. So when you come into school, hopefully in a week or two, you're going to hear us say 6 feet, 6 feet, 6 feet. Come on, you can't be near each other. Okay, 6 feet social distancing. Wearing a mask. Wearing masks. Okay. Initially, when we first did this, they shut everything down. So they shut down schools, everything. Restaurants, everything shut down. And that took the time so that the virus then was like, it wasn't able to spread as quickly. And so it slowed down, and then we had this nice little curve. And that was their goal. All right? You are going to explore our city and the data, and I give that to you in lesson 4, okay? You're going to explore this all in the data, and you're going to determine in our local city of Yonkers and our county of Westchester, you're going to plot out the data I give you, and you're going to see, did the curve flatten or did it not? And then what we were going to, think about was these mitigation strategies successful? Okay? So, having said that, that was an overview of what the intent of this whole lesson is. I'd like to share with you quickly is the lesson that you will be receiving. So the first one is just an overview again, kind of what I just kind of talked about was the flatten the curve concept, all right? These 3 videos, you will have these links to watch. One of them is me, enjoy it. And the other one is this mathematician. I'm going to just kind of glance over and show you him on the computer. And a third one is another math expert, okay? Guys, this one here, the third one, is a little complicated, but guys, it's not about you learning equations and all this, tough terminology. It's about you listening and getting the graphics and the idea of what this growth of an epidemic, what it means, exponential growth of an epidemic, okay? They've got pretty cool visuals on here. That's why I'm sharing them with you. You will then have to write a little short essay explaining some of these things about it. What is exponential growth? Can you compare linear growth and exponential growth? I kind of just did it with you. Okay, so you're gonna put it in your words, okay? And the last thing I really liked was the narrator in the third film had these 2 sentences. And I want you to reflect on this. But if no one is worried, that's when we should worry. And the other one was, the only thing to fear is the lack of fear itself. What do you think he meant by that? Okay, so this first video, and let me show you that video real quick, is on my computer, if I can get the camera to turn, and kind of take a look-see. All right, take a look. The first video, like I said, you will look at, okay, is this guy. He is a mathematician from Oxford University. He's pretty awesome. Tom rocks math, and I find these things by accident, but you know me, I like looking at educational days, and I like the graphics he does here. So just so you
reproductive
can
number R0 or R0.
Love his accent too. 3. So he's pretty interesting, and it's only a 3-minute
have the disease
video.
In this pretend scenario, then I would expect to infect around 3 other people.
So he shows the simulation.
Now there are 4 of us that have the virus, but the good news is that I'm starting to feel a lot better. So whilst I'm no longer infectious, the 3 new people that I've passed the disease on to will then go on themselves to infect another 3 people. He's a pretty cool looking
character, right? So now he shows the demonstration again. Pretty cool. So you're going to look at that one, all right? The next video is the exponential growth video. And this man actually models it like kind of what an exponent.
Hard time really recognizing what it means sometimes.
See how it's going?
We can anchor on a sequence of small seeming numbers.
See?
And become surprised when suddenly those numbers look big. Even if the overall trend follows.
Now, I wish I had the capability of demonstrating all that on a graphic. So that's why I want you guys to watch that. That's pretty cool. Okay? All right. And then that's the first assignment, is just to share those 2. And again, that video is all of 8 minutes or 9 minutes long. You can handle that. The next one is a second assignment is I want you to take a look at some charts and data that I happen to find from a newspaper article from Syracuse, okay, and it was which is upstate New York. And I like the way, and I have the link in the assignment, the way you can scroll over this. This is their data collection, New York coronavirus tests and positives, and notice how the numbers change per day. Like they kind of give you the dates and the bar graphs, and clearly look at this. Look at this. How it just rapidly goes down, okay? And so this is a kind of, you can play with this, and you can use this as a model for your own graph if you can, when you go to make yours, okay? I just like this interactive kind of site. And there is a couple of questions on lesson 3 where you have to compare the numbers for the data coming from this chart. So in other words, you're going to have to go to this site and fill in some answers coming from this. So that's New York hospitalizations during the coronavirus. Okay? So that was pretty cool. So I just wanted to share that with you. And that lesson is called proportional data. All right, this is the proportional data lesson where you have to fill in info. Okay? And then there was one more assignment. You will look at one of the CDC sites that compares the United States COVID-19 cases and deaths by state. And I thought this was, notice it started from January 21st on. I thought this was a really cool site because the graphics are awesome. You go over the state and it literally, here's Montana. It tells you the total cases and it's updated all the time. So this is presently today. And how many cases, in the last 7 days. And then what I really like is the cases per 100,000. That's a proportion. And you can compare to different states. So Montana has per 100,000 people, they have like 1,100, let's say, 1,100 cases. Whereas if you zoom over to New York, our cases per 100,000 is 1,906, okay? The dark orange is significant. Let's see if I can get down to the key. The key is down on the bottom, cases in the last 7 days, and how, the dark orange is more significant. In other words, Florida, not good, okay? Texas is not good. California, not good. So I want you to kind of explore this, and your assignment it's laid out in this document. The assignment has you looking at 5 different states, okay, and filling in their color. And what was the math behind that color? What was meant by that? Okay, you have to answer a little question about comparing Wyoming to New York, and then write a summary about proportional relationships. So doing a little bit of writing with this math. And what conclusions can you make regarding shutdown of most of our daily places, our stores, our schools, our churches, our businesses, etc. Okay, and again, we have a rubric that will go along with this. All right, so just another, I want you to, explore as much as you can. I think this is pretty cool. This is the CDC national site, and the numbers, amount of cases, etc. And this was updated September 27th. And today's date I have is September, I think, 27th. So pretty cool. So have fun. Notice how you can just keep exploring. And this actually is different than when I initially made the assignments or thought the assignments and found this. I was looking at this back in like April. And the states looked very different, the colors. Okay, and I bet you in 2 months from now, we'll look again different. So through the year, we're going to revisit this and kind of explore. All right? Then the other one, which is kind of a cool activity, and I'm going to go back down to my desk, is to show you the lesson on making face masks. Okay? And how would you go about making a face mask? So I wrote a little scenario here. Your family and friends need to have face masks. Remember when we first, couldn't go out, you had to have face masks. Where are you going to get a face mask from? So you were, kind of looking for face masks. So I actually went out and I bought fabric and I kind of designed my own. So this is your mission, is to design your own face mask, given this piece of fabric with the specific dimensions, okay? I have it in here, 54 inches wide by, let's say, 3 yards long, such as, so let's say you take a nice big piece of fabric, okay, and envision what you can do with this, and how many face masks can you make, okay, out in that particular size, such as 9 by 8 inches. So 9 by 8 inches is, let's say, this big, okay? I use some baseball things. And you want to take a very large piece of fabric, 54 inches wide by 3 yards long, and you want to figure out how many of these can you make, okay? I left you a spot here for you can draw it out You can do it math, however you want to figure it out. You're going to figure it out in here. And then you're going to chart it and say, okay, in so many days, I can make this many face mask. X being the number of days, Y being the total number. Can you come up with how many you are making per day? Is the rate constant? So this is just a basic review of our linear, okay? And you're going to graph this. And then you're going to answer about your little prediction of how good your business is, okay? So that's assignment 3. Assignment 4 will be to, is the culminating activity, and this is the one I really, really like. This is where you're going to take the data, and you're going to make your own graphs, okay? And you're going to write a conclusion. Once you have this all done, and I did the data on a base of 4 days averaged. So basically, they took the numbers in groups of 4 days, average, 4-day average, 4-day average, 4-day average. Otherwise, the data was just extremely overwhelming. And in order for you to get a pretty decent graph that looked like, good, 2 months long or so, or what is about a month and a half long, I wanted to condense it a bit so you can see the numbers and create your bar graphs, just like the one you will explore and investigate on that website. So here's the data. I painstakingly every night was writing this down, and then I realized I could go to the CDC site and come up with them anyway, okay? And then, so we have Westchester County and the city of Yonkers. So you're taking this data and you're going to make 2 different graphs and how you will represent it. Each one of these assignments has a rubric with it, and it's basically 4 activities that will totally bring your knowledge of COVID-19 and how we Americans, we New Yorkers, were able to flatten the curve or not. And were our mitigation strategies successful or not? Okay? So, and after you finish all this, you guys could write a resume and apply to be a CDC person, the Center of Disease Control, because this stuff is not easy, but it's awesome. It's sadly, it brings to you, what are we living? Why are we living the way we are living? What is going on in America or in the world that, with this pandemic? This is historic. You are making history. We are going to be in textbooks for the rest of our lives, our time period. Our children, our grandchildren, all that will study how did the scientists handle this pandemic and were we successful? So I wish you luck. I can't wait to see your items. This is going to be fun, okay? And that's it. The COVID-19 math, the math behind flattening the curve. Best of luck.